Okay, so hi everyone, we are back with a question. So today we'll be doing this block on a wedge question where the block is sliding down the wedge and there's no friction between all surfaces, meaning that the wedge is moving along the table as well because the wedge is not fixed to the table. So we'll be doing this via two ways, right? We'll be doing it firstly via the accelerating reference frame, right, which is also known as the non-inertial reference frame. Then we'll be doing it in the inertial reference frame, which is the one that in the lab frame. So it's a fixed frame, right? Where the velocity is zero, the acceleration is zero. So it's a fixed frame. And we'll arrive at more or less the similar equations, just that you might think that personally, I find that formulating the equations in the accelerating reference frame is easier to see, although you may say it's conceptually tricky. So it's a trade-off between whether you want a more conceptually simple in a fixed frame or whether you want um, a more formulating the equations to be simpler in the accelerating reference frame. So I'll give you both options. I'll present both options and for you to kind of decide for yourself also. It's up to personal preference too. So, okay, so first of all, let's do it in the accelerating reference frame. So, okay, so we'll be doing it in the accelerating reference frame, but before that, right, um, it's always good to 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 get a sense of what happens, right? And to get a sense of what happens first, we will do it in the fixed frame. So let's do it in the fixed frame, right? Before we jump into the accelerating reference frame. So this solution will be based. The first solution we do will be based on the accelerating reference frame. But for now, let's just take a look at what happens if we think of it in the fixed frame first. So there'll be the block, right? Block of mass M, wedge of mass capital M, and there'll be what forces are acting on the wedge. Firstly, there will be a normal contact force between the ground and the wedge, and then there'll be another normal contact force between the wedge and the block. But actually, the normal contact force between the ground and the wedge is not really interesting because it will always adjust accordingly to make sure that the wedge does not sink into the ground. So in a sense, it's only there. The sole purpose of existence is to cancel the vertical component of this end, right? And so because the wedge never flies off the ground, the wedge never accelerates vertically. So it's not interesting to consider the normal contact force of the between the wedge and the ground. So we'll be only interested in this end over here. And because this is the only force acting on the wedge, the horizontal acceleration will be to the right. So let's denote it with A capital M, right? A subscript M. And yeah, so so the other forces that are acting on the block this time, right? On the block, there'll be a normal contact force between the block and the wedge, and there will be a mg also. So there'll be mg, gravitational force, and yeah, that's pretty much it. But the reason why I prefer the accelerating reference frame is because in this case, if your block is sliding on the wedge and the wedge itself is moving, to me that's a little bit complicated to understand the constraints. So I prefer to go into a reference frame where the wedge itself is stationary. That way, right? I account for all the I account for the constraints. It's easier to account for the constraints basically. So yeah, so let's move into a reference frame where the where the where the where the block is stationary. So in the accelerating frame, right, we have a block that is stationary. So now this block is stationary. And we know that because the block is stationary, right, the reference frame is accelerating to the right at an acceleration of am. And if you're in an accelerating reference frame, then Newton's law, right, F equals ma, will not hold strictly speaking, right? But you have to add in some additional fictitious forces, right? So you have to add in some fictitious forces to make the equation hold true. So that's the consequence of going to the accelerating reference frame. And this, and we will cover, right? We covered this fictitious force in another video, in the previous video. So yeah, so with that, once again, we have the mass M over here and the big wedge M. And now we can solely consider forces on the, the, the block. So what are the forces on the block? So first of all, there's a mg, then there's a normal contact force, right? And this N is the same normal contact force between as the force is the same normal contact force that the wedge experiences from the block. Okay, and yeah, and on top of that, there'll be the non-inertial force, which is going to be towards the left, and it's going to be the mass m times acceleration am. So the green forces are the real forces. The green forces are the real forces over here. And the blue force, right, is the force in the fictitious force that is caused by the accelerating reference frame. Yeah, so now we can formulate a few equations, right? So let the acceleration of the block be, let's assume that the acceleration of the block is ax and ay. So the acceleration of the block will be ay, and this one will be ax. Then we can go ahead and formulate our equations of motion. So the angle here is the angle of the normal contact force is n with the vertical. And one way to check that you got the correct angle, right, whether you know whether it's theta or 90 degrees minus theta, is by letting theta go to 0. So in this case, you see that if theta goes to 0, right, then clearly, if theta goes to 0, then clearly this normal contact force, right, will be pointing vertically, right? So hence, that's how I know the angle theta is the angle between the normal contact force and the vertical, instead of being like the other way, instead of being with the horizontal. So one way to check angles easily is to use limits, the extreme limits between 0 degrees or 90 degrees. Okay, so anyway, so in the accelerating reference frame, let's consider AX. So the mass, so MAX horizontally, MAX equals to your non-inertial force MAM plus N sine theta. Okay, then our vertical will be MAY equals to mg minus N cosine theta. Then our okay, then now we have we have quite a few unknowns. We have 1, 2, 3. We have 1, 2, 3, and 4 unknowns. We have 4 unknowns: ax, ay, am, and n. So we need 4 equations. So whenever you solve mechanics questions, it's actually a matter of finding first of all defining the variables, defining all your variables, right? And then forming equations. And if you have n variables, right, you have n variables, then you need n equations. So if not, you'll be left with some degrees of freedom, loosely speaking, most of the time. Yeah. So and then usually you have quite a few equations. You can go out to 4 or 5, and usually it caps around there. If you're going beyond that, then there usually is some trick involved. Like for example, the Lagrange multipliers, which we'll talk about in another video. And usually it's just a matter of solving these simultaneous equations. They could be linear, they could be non-linear, but most of them, they are just linear equations. And then from there, you get the answer. So at the end of it, the variable that you're interested in this case, we're interested in AM, right? We write it in terms of the constants. So that's the goal. Yeah, so now we have 2 more equations. The first one we can find from the constraint, right? That because the block is now stationary, right? Because we're in the accelerating reference frame, then we know AY over AX equals to tangent theta. Yeah, so this is the simplicity of this third equation is due to the fact that the block in this accelerating reference frame is stationary. Sorry, the wedge in the accelerating reference frame is stationary. And lastly, there's one more equation and it involves n. So how do we haven't wrote am so far, right? So for am, right, it'll be n sine theta equals to m am, to big M. And where does this come from? This comes from over here. This comes from the equation here. Right? So that one we have to, so the last equation, it does come from the fixed frame, which is why we started off by drawing the fixed frame diagram. So just because we're doing accelerating reference frame doesn't mean that we can just completely forget about the fixed frame. And often we have to reference back to the fixed frame, to the lab frame, because that's where we can get our non-inertial, that's where we can get our AM, our non-inertial force. Okay, so let's go ahead and label these equations 1, 2, 3, 4. You may be tempted in your practices to not label the equations, but perhaps I could advise to, in fact, label equations and present things neatly as if you're going to in the competition, because if you are used to loosely writing down, there's two downsides. One is in the competition, you might be put off by the amount of labeling that you need to do and the presentation of instructions. And the other downside is that if you meet an error, then it's harder to trace back your source of the error, right? And if you go ahead and check the units in this case, right, for each of the 4 equations, let's just do it for the third one. The units on the left is meter per second. Acceleration over acceleration gives you a constant. And the right hand side, tangent of an angle is unitless. So it's also very good once you establish the equations here to check for units. And now for these 4 equations, it's just a matter of solving them simultaneously. So after you check that all the units for all the 4 equations is correct, right? It looks correct from now. Then you can move on. So let's go ahead and solve them simultaneously. So there are multiple approaches to solving them simultaneously, and it's often good to when you check the solution, when you check your equations against, when you check your equations of motion, right? So these are known as the EOM, equations of motion. We check equation of motion against the answer key, they should match. Yeah, and usually the steps that the answer key takes to solve these simultaneous equations is going to be something that you will not follow exactly. So once you check the equation of motion is correct, I encourage you to also to derive the final answer from your, but solve the simultaneous equations by yourself, because the answer key will most definitely do it in a slightly different way from you. And it's also good practice for you to develop your own style of solving simultaneous equations. Yeah, because not every one of them is as straightforward as substitution and things. So yeah, so I'm just going to do it in my style, but if you want, you can go ahead and pause the video and do it in your own style and check the final answer. Okay, so in my style, right, for equation 1 and 4, I can substitute AM into there. So I can substitute n sine theta into there. So it'll be AM AX equals to M AM plus. Okay, then from here, let's go ahead and do 2 and 4. So what I'm trying to do over here is I'm trying to eliminate the n's first. Then we have left with 3 variables and 3 equations. Okay, so that would be okay, and then from there, okay, now we see that equations, we can label them 5 and 6. And now when you take 6 divided by 5, we can match it up with 3. So okay, and from here, we substitute 3 inside. So we have And let's go ahead and rearrange it. And then from here, we want to make AM the subject of the formula, right? So let's go ahead and, so if we bring this term over, we bring this term over to the left-hand side, then we get M sine squared, right? And factorize out AM, then we see that the M sine squared, M sine squared, and the M cosine squared actually combines to just form M. And the right-hand side is just mv sine theta cosine theta. And lastly, we can write, so this is just mv sine theta cosine theta over m sine squared theta plus big M. So and we're checking the units, right? We see that in the numerator there's a dimension of mg, right? In the denominator we have the dimensions of m. So in the end the units is g. So yeah, so this way it seems like I've just done it quite, it may seem that I've done it quite smoothly, and the reason is because I have worked this out. And in fact, while preparing this question, I have gone through many times of misformulating the equations of motion and making numerical errors when solving the simultaneous equation. But yeah, so it's completely natural to be stuck on such a question due to so-called dumb mistakes by having wrong equations of motion or making substitution errors. Yeah, so let's just go through a broad overview of what I did and the reasoning behind it. So if I look at equation 4, right, it gives me n in terms of am. So immediately, if I substitute equation 4 into equations 1 and 2, then the n effectively disappears, right? So if we look at equations 3, after substituting in, if we look at equation 3, 5, and 6, right, then we see that they don't involve m anymore. And the only unknowns left over are ax, ay, and am. And yeah, and theta is a constant, remember? So so from there, I then further went on to eliminate ax and ay, right, by dividing 6 over 5. And from there, because 6 over 5 is ay over ax, which equals to tangent theta, so that gave me this equation. And from there, it's a matter of rearranging to make am the subject of the formula, because remember the goal of the question is to find am, and in the end we found am in terms of all the constants. So yeah, that's the spirit behind most mechanics questions anyway. Yeah, so that's the way to do it using the accelerating reference frame. Now let's do it using the non-accelerating reference frame. So so the non-accelerating reference frame, I'm just going to take it from the answer key, right? So the answer key is this, and first few things you notice, right, is that so they define ax, ay, and am. Just that now, there's no non-inertial force. So you see the only forces acting on the block is these two forces. There's no more non-inertial force, no more fictitious force. Okay, so vertically they get this equation, and horizontally they get this, and then for the block they get this, and the only area where it differs from right, is besides having the horizontal one over here, where we add an additional fictitious force. The main reason, right, why I used the accelerating reference is because I wanted to avoid this equation, because to me this equation seems a little bit complicated, right? Yeah, but perhaps for you it's intuitive, I don't know. So that was just for me, where the denominator is the combined movement. That was a little bit off-putting for me conceptually. So I preferred to go into the accelerating reference frame to make the denominator simple. And from there, there are 4 equations, the highlighted ones, and then from there, they went on the substitution, right? I won't go into the details, right? Yeah, this entire document is in the website below. So yeah, so yeah, with that simple example, that's how we use a non-inertial reference frame. So yeah, I hope you had a nice, see you in the next video.